Hello again. We're going to continue with the definition of the process control block, the PCB. As I mentioned in the last video, the PCB, you can see it as the soul of the process. It's what literally makes the process alive. And I wrote you this equation that process equals PCB plus program. Okay, you can always see this way. So when you start executing a program, we add to the program a PCB, and therefore it becomes a process. So what's inside this PCB? It's basically everything about the process. I always told the students that you can imagine the PCB to be the kind of the DNA of the process. So when you take it, when you can have access to it, you can know everything about the process. Starting from where it begins, where it ends in memory, in which state the process is now, the program counter, where is it inside the process code, of course. The values inside the CP registers, and so on. So you will see here the process state. So whether the state is running, is it ready, is it waiting, right? You also have the program counter, which points to which line is being executed now in the code. So the lines of code. Okay, so which line is it? Program counter. Okay. The CPU registers, the values inside the registers. The values inside the registers. Okay. Why? We'll talk about it when we talk about the context switching. The CPU scheduling information. So what priority is the process is in if you are following a priority scheme. Okay. In which scheduling queue? Is it ready? Is it waiting? So the queue that the process belongs to. Okay. I'll talk about the queues in few minutes. Also, you have memory management information. So what is it? As I mentioned, where does the process start in memory? Where does it end? And so on. So basically, the memory allocation for the process. Okay. And the, of course, accounting information, that would be, the accessibility, the CPU that is being used, the time allocated for it, and so on and so forth. Okay, so everything that you will find in chapter 5 is also stored in the PCB. Also, the I/O status. Okay, so which I/O device is allocated to it, which open files does the process has, and so on and so forth. Okay, so are those like all the items that are stored in there? No, those are just examples. You have much more information that you would find in a PCB. All right. The PCB is like a struct in C. Okay, it's literally implemented as a struct. How about the threads? Everything that you have programmed so far, okay, is nothing but processes with a single thread of execution. So you didn't have multiple threads. Now, when you have a process, and this process has code like that, lines, If you have a single thread, you have a single PC program counter pointing to the code. Okay? In multi-threading, you have PCs equal to the threads you have. So if you have two threads, here they are. So the first thread is executing this one. The second thread is executing that one. The third thread could be executing this one, and so on. Okay, so in multi-threading, you have a number of program counters equal to the number of threads you have. So what does it mean to have a thread? You can see the thread as line of execution, sequence of execution. That would be a thread. Okay. Then for the lines of code you have, you can execute it multiple times, each and every one of them with its own PCs, okay, a program counter, and of course its data, so the register values and so on. All right. So that's the idea behind having multiple threads, as you will see intensively and in details in chapter 4. Okay. Of course, if you have multiple threads, then as I mentioned, you need to store the information of every thread, the details. So its program counter, the register values, and so on and so forth that are related to this thread. All right, this is going to be very detailed in chapter 4. So the process in Linux looks like this. See here. You have a PID. This is a unique number, okay, that represents the running process. You can see it as the ID, the civil ID, okay, of the process, okay, and it's an identifier for it. For those who know databases, it could be like the primary key of the process per run, okay. Also the state, and look how we define the state, a long value. Okay, so this long value will tell you whether the process is running, whether it's ready, whether it's waiting. Okay. We also have unsigned time slice. We called the time slice before the quantum, if you remember. Okay, time slice. So the time allocated for this process is an integer, of course. Okay, so 2 milliseconds, 3 milliseconds, 5 microseconds, whatever that is, the unit that we are dealing with. Okay, this is the time slice. We have here who's the parent of the task and who are the children. Every process has a single parent, and it could have 0 or more children. That's why the parent in Linux is just, a task, as you can see, a task struct. But the children are a list of the tasks that we have. And, a list of files that we are, dealing with. This is actually a pointer to an array. Okay, and we have here the address space that this process is dealing with. Okay, so this is how the process is defined in Linux. Not the process, but the PCB, I mean. Okay, and then you have here the currently executing processes are nothing but, something like that. Here are a list of executing processes. And then this is the current one that is running right now. How about the others? They are running, but not right now. How is this possible? That would be if you're working something like round robin, if you're doing time share. So that's how, it is done in Linux. Okay. How about the scheduling of the process? The scheduling of the process is done through what we call process scheduler. Okay, process scheduler. What does it do? It selects among available processes. And I'll stop here, okay, and go back to this diagram. Look at that. So, if you look at this diagram, you will find few terminologies that is written there that we didn't really discuss in the previous video. So look at this here. If you have few processes, P1, P2, P3, and so on, in the ready queue, the one who picks the process to execute is the process scheduler. Of course, we call it CPU scheduler or short-term scheduler, as you will see it later. Okay. But then, in order for the process to actually run, we have something called dispatcher that takes the PCB out of the ready queue and puts it as in the running state. Okay, so the one who chooses is the scheduler. The one who executes the choice is the dispatcher. The relationship between the scheduler and the dispatcher is the same as the judge and the police. Okay, so the judge makes the decision and the police makes it happen. Okay, same here. You have the scheduler. The scheduler will choose which process to run right now. Okay, and the dispatcher will take the process and put it into the running state. I also have to tell you something here, that this scheduler is running almost in each and every transition that you see. Okay, so why would it run when an admission happens? Because maybe the new arrival has a much higher process priority compared to the one that is running. So as soon as we have a new arrival, the scheduler has to run. Okay, what else? When the running process, runs out of the allocated time, so the time slice, now an interrupt happens and the process leaves the running state and goes back to the ready, and another one has to be picked up for it to run, which means, when an interrupt like that happens, the short-term scheduler or the CPU scheduler has to run to select another process. Okay, when a process finishes and exits the system, okay, the CPU scheduler has to run. Why? Okay, because now the processor is empty. The CPU is idle, so to say. Okay, so this means that you need to choose another process to be assigned for the CPU for it to be busy. Okay, all right. All those are very clear and straightforward, but look at that. When a process gets waiting, okay, so it means, it asks for an I/O and then it waits for the I/O to happen, as I explained it in the last video. Of course, the CPU scheduler will run to choose another process to get the access of the CPU and, for the CPU to be busy. But then, when the process that is waiting, okay, gets back to the ready after the I/O is done, the CPU scheduler runs again. Why? Simply because this running one, this waiting process, when it goes back to the ready state, it might have a much higher priority than everybody else, including the one that is running, right? Which means now that the CPU scheduler has to look up the priorities again to see whether the one that is running has the right to keep running, or will it be replaced by the new process that just left the waiting and became ready. Okay, so this is very, very important to understand this whole life cycle of the processes. As you can see, the CPU scheduler, or what we call the short-term scheduler, is working all the time. So it works when there's an admission, it works when an interrupt happens, it works when a process terminates, it works when the process initiates an I/O request. It even works when the waiting process is done waiting, because the I/O that it was waiting for is done. This means that the short-term scheduler has to be extremely fast, because otherwise it's going to be a bottleneck for the operating system. Because literally in each and every single event that happens here in this life cycle, the short-term scheduler will be initiated again, right? Which means that it has to be extremely fast for the operating system not to be slow. We don't want that scheduler to work as or to be as a bottleneck for the whole operating system. How does this short-term scheduler work and so on, we will see it in chapter 5. Okay, let's go back here. Okay, so the scheduling of the process happens in, as we have mentioned before, queues. Okay, so for the ready state, we have a ready queue. For the waiting state, we have waiting queue. Okay, for the running, well, if you have a single CPU, you don't need a queue, really. It's a one running process per time. If you have multiple CPUs, so you have multi-processing system, you might be having, those running queue that would make sense then. Here you have the ready and the waiting. Here it is, look. So here is the ready queue. Here is the head. Okay, and this head points to the PCB7, and PCB7 points to PCB2, a linked list, right? And if one of the processes becomes running, you don't move the whole process, by the way. The code remains where it is in memory. You don't move it anywhere. Okay, what happens is that the state inside the PCB gets changed, and therefore it moves from the ready queue to the running state. Okay, same here with the waiting. As you can see here, you have PCB3, PCB14, PCB6. They're all waiting for I/Os for them to happen. As soon as the I/O of PCB3 finishes, then PCB3, you will not find it in this queue, and it will be added here. So you will find, it doesn't have to be in this particular location, okay? But I mean in this queue, it's going to be PCB3, it will be here, okay? Again, the process itself doesn't move from anywhere to anywhere. It's the process control block that moves, all right? And here is the, the queues. So this is another perspective for this life cycle. You see this life cycle? We have here a different perspective of it, another way to see it. All right, so what happens here when the process gets into the system, it becomes inside the ready queue. All right. One of them in the ready queue, the processes in the ready queue will be selected for execution. So it's allocated the CPU here. If the process finishes, it leaves. If it doesn't finish, then we have one of those possibilities. Either you get an I/O request, so the process is asking for an I/O. So the process inside the PC, like that has the control of the CPU, it will be inside the waiting queue, and another process will get access to the CPU. Okay? All right? When the process in the I/O waiting queue here, when the I/O finishes, okay, then the process goes back to the ready queue to wait for its coming turn. Another possibility is that the time slice expires. So as I mentioned, the quantum in something like round robin, okay, the quantum would be, let's say, 2 seconds for every process. Of course, it's not 2 seconds is too much, but this is just an example, okay? So let's say it's 2 seconds. So when as soon as you run a process, as I mentioned, the timer gets 2. Okay, after 1 second, the timer becomes 1. After another second, the timer becomes 0. When the timer becomes 0, an interrupt is created, and the process inside the CPU now leaves the CPU and it goes back all the way to the ready queue. Something else could happen is that the CPU creates a child, as you will be seeing in this chapter. Why? For the parent and the child to execute concurrently. Okay, so when the CPU creates a child, there is a possibility here that, the child termination waiting queue. So the parent will wait for the child to terminate before it terminates. So you tell me it's sequential. No. What's happening here is that here is the process. Okay, so the process in this point of time, it creates another child. So now the two of them are working concurrently or in parallel, depending on whether you have multiprocessing or not. And then here is the termination point. This parent, after this point, will terminate. It will not terminate until the child finishes, and then, the child terminates, so the parent will also terminate. If this doesn't happen, we will end up having either a zombie process or an orphan process, as you will see later. Okay, when the child terminates, now the process can go and wait for the ready queue again or terminate depending on the need. Now also if the process is waiting for an interrupt, so what kind of interrupt? Press any key to continue, or something like that, any interrupt that would happen. Okay, so as soon as it waits now for the interrupt waiting queue, waiting for its own interrupt. When the interrupt occurs, then the process now waits for in the ready queue for it to be selected again. Okay, all right, we're gonna stop here and continue with the in the next part.